So now, in this next example, I want to do is imagine you have a satellite orbiting what they call an Earth that is basically smooth Earth that doesn't have any mountains. It's just a perfect sphere, and it's on a circular orbit. So we have here's Earth. Here's Earth. Here's Earth. And it has a certain radius, right? The radius of Earth. And the satellite is here, right on the surface. Imagine there are no mountains and the Earth is a perfect sphere, and the satellite just goes around Earth with a perfect sphere in a perfect circle of, well, since hovering right at the surface of the Earth, then it will have a radius. It's going in a circle of radius r, and r is the radius of the Earth. So what are the forces on this satellite? Who is pushing it down? And why isn't it colliding with the surface of the Earth? Well, it's moving fast enough. So it's being pulled down by the force of gravity here, the force of gravity. But every time it falls, it is here because it has an initial speed this way. So it is constantly falling, but every time it falls, it has moved this way. By the time it falls, let's say to here, it has moved to here. By the time it falls to here, it has moved to here. And it's always constantly moving. So we conclude that the force of gravity is the only radial force of gravity, and that has to equal to the mass times the acceleration, which is v squared divided by r. The force of gravity on an object, remember, it will be near the surface of the Earth, it's just mg, mass times gravity. And then you have mv squared over r, so this cancels, and you get v will be g times r square root. That's that. And so what speed would it be? Hypothetically, if the Earth were just bold, like no mountains, nothing, and it's just smooth, perfect sphere. Well, v would be, g is 9.8, and this is 6,400 meters, 6,400 kilometers, so it'd be about 6.4 times 10 to the 6 meters square root. What would the speed be? So let me get my calculator here. Just get an approximation. So 9.8 times 6.4 approximately times 10 to the 6th power. Oops, 10 to the 6th, not second. 6th power. Let me take the square root. And I get about 7,900 meters per second. Just write it down. 7,900 meters per second, which is approximately in kilometers per hour, it would be 28,510 kilometers per hour. And then in miles per hour, it would be approximately that number divided by 1.6. So that's 17,800. 17,800 miles per hour. Let me make sure that I have the correct answer, just like the book. I didn't make any mistake. So in the book, they estimated to be 16,000. They estimated to be 16,000 because I used 6.4, they used 6.37 for the radius of the Earth. So slightly less. So, but 16, 17, 18,000 miles an hour if you were to orbit like so. The next thing we want to talk about is the fact that the Earth is a non-inertial frame of reference, and Newton's laws, they hold in an inertial frame of reference. Because the Earth, remember, an inertial frame of reference is a reference that doesn't accelerate. As I stand in this room, it seems like I'm not accelerating, But actually, the Earth is spinning about its own axis and going around the sun also. So, would that create a problem? Well, let's see. Let's see here. So imagine I'm here. I'm here. And I'm sorry. This is Earth. The Earth is going around. Here's a scale, and I'm here. I'm here, standing on the scale. So what are the forces on me? What are the forces on me? The forces on me will be, let me get this. The forces on me will be, I'm standing on the scale, so there is the normal force from the scale on me, and then there is mg, the mass times gravity, the pull of the Earth on me. And that's it. And we usually say the normal force is equal to mg, and that's my true weight, if the Earth is not spinning at all. But consider the fact that the Earth is spinning, so if the Earth is spinning, then these two forces have to combine to give me a centripetal acceleration toward the center of the Earth. And so I conclude that the net force in the radial direction will equal to the mass, my mass, times the acceleration toward the radial direction. Times the acceleration toward the radial direction. So what's the net force in the radial direction? There is a normal force upward. And then, well, if I consider the downward to be negative, then this will be minus, because the radial direction is down. So the normal force minus mg, and yeah, the normal force minus mg is equal to minus m times the acceleration in the radial direction. So I get the fact that the normal force then will be mg minus the mass times the acceleration in the radial direction. So what is that acceleration in the radial direction if we were to consider it? Well, the acceleration in the radial direction will be mv squared over r, right? Where I'm spinning with the Earth. But, I'm sorry, not mv squared, it's just v squared over r. That would be the acceleration. But v is omega r, is omega times r squared divided by r, and so I get omega squared times r. That's something we knew earlier. But what's omega? Omega, the Earth makes one revolution every 24 hours. So let's see what omega, what the acceleration would be. The acceleration would be omega squared times r, and r is let me write 6.38 times 10 to the 6 meters. Okay. I used 6.4. Let me use the one that I just saw, 6.38, the more accurate. So what's omega? It's, well, you get 2 pi radians every 24 hours. But then I need radians per second, so that would be 1 hour for every 3,600 seconds. So what would the acceleration be? Let's see, because this will be the effect. I mean, the normal force, my weight would not be quite mg, it would be mg minus a little bit. Let's see how much is that little bit. That little bit, how much is it? So I would have 2 pi over 24 over 3,600, and then you have to square it and then multiply by the radius. So I have 2 times pi, 3.14159 approximately, over 24 over 3,600. Then I have to square this number, very tiny, and then times 6.38 times 10 to the 6th power. So the acceleration will be 0.0337. 0.0337 meters per second squared. And compared to the 9.8, so if you want, it would be this, m times g minus this acceleration. So my true weight would be m times 9.8 minus 0.0337, which is very tiny. Basically negligible, unless you're doing something much more accurate than everyday experience. So I will pause here. I mean, we can talk more about non-inertial frames of reference, but it's not a topic that we want to discuss, at least in our book or in this course. Uh, at, Not a topic we want to discuss at any greater details than this. So um, we'll come back next time and we will do few problems from the end of the chapter, chapters 7 and 8, and that will be the end of these chapters. And then the next topic will be a complementary to Newton's laws. We'll use Newton's laws in math to talk about the concept of conservation of energy and then the concept also of conservation of momentum. And we'll find that it's a really powerful method, that there are problems that are intractable if you want to use Newton's laws directly. Uh, uh, but they're very easy. They are one-line calculation if you use conservation of energy and momentum and or momentum. All right, I'll see you next time.